The thing that I enjoy most is being with a class of students. I teach mineralogy courses at the upper division and graduate level at the university. I also teach general introductory science courses for freshmen and some courses with other departments in my specialty. A mineral is an inorganic solid that's characterized by a definite chemical composition that may have a range, but it can be expressed as a formula, and a fixed atomic arrangement. That is to say, there is, for example, a class of minerals called feldspars. They're the most abundant minerals in the crust of the earth. All of them have essentially the same arrangement of atoms, but they differ in their chemistry. And there is a range of chemistries that defines what feldspars are. Well, the most common minerals are silicates, and there's an elaborate classification for silicates that tells you something about the way the atoms are arranged, the way the crystal structure is built. For example, this piece, I don't know that you can see it well, but it's a pale green mineral called olivine. This particular nodule came up in a lava flow in the Grand Canyon from probably several hundred kilometers deep down in the mantle of the Earth, where olivine is one of the major constituents. So we learn something about the Earth at great depth by seeing what comes up in volcanic eruptions. In olivine, whose formula is MgFeSiO4, where Mg and Fe can substitute for each other. That's the range in the formula. The formula has an SiO4, which says that it contains a single silicon surrounded by 4 oxygens, not linked to any others. Silicates are compounds that are made of one or more metal atoms combined with silicon and oxygen. The silicon is invariably surrounded by 4 oxygen atoms, and that makes the silicate anion. There are other common ions, other common compounds in nature, sulfates and phosphates and borates and other sorts of things that we look at. A crystal is a solid that has a particular atomic arrangement and a definite composition, may be inorganic or organic, and it's bounded by plane faces. In practical terms, we don't pay much attention to that definition, because when we work with crystals, we often have to fragment them into small pieces, and we still call the pieces crystals, even though the plane faces are gone. This is a mica, and this is the crystal structure of mica, and you can see that it's made of layers. In this, the formula for a particular kind of mica would be KAl2Si3AlO10OH twice. Now, what all that tells you is that the silicons are linked together here into sheets. It's made of layers, and the potassiums in between are not strongly bonded to the layers, and so it splits off there. Here I've got a colorless sheet of mica. It's called muscovite. The formula here has potassium, aluminum, silicon, and oxygen. None of those are elements that cause color. If I take the aluminum out and put in magnesium with just a trace of iron, then we start to get a little bit of a bronzy color, and the more iron replacing magnesium results in this very black mica called biotite. Colors are not always good diagnostic tools for minerals. This piece of fluorite, calcium fluoride, is the formula CaF2. Fluoride has no elements in it that normally of themselves would cause color. When light, photons, hit that electron, they will absorb some of the energy in the light. So what you see actually is the light that is left after the electrons have absorbed what they don't take. That's called a color center. This mineral is kyanite. You can see it's a sort of a bladed looking mineral that's a mottled blue in color. The composition ideally is Al2SiO5, which has no transition metals, but there is a very small amount of iron in this, and this is the other means by which color is commonly caused in minerals. It's called charge transfer. There is both iron 2+ and iron 3+, two different oxidation states, and as photons hit an iron 2+, one of its electrons can be knocked to a nearby iron 3+, reversing them. The 2+ goes to 3+, the 3+ goes to 2+, and of course that removes that energy from the spectrum. And then what's left is this mottled blue. The iron is not evenly distributed at all, and so that's why it comes out as sort of a mottled blue-white. There's another mechanism that involves transition elements. In fact, two others that involve transition elements, the elements between scandium and zinc. Those are the elements that have d orbitals in them. Now, if I were to put an element like iron with d orbitals into an environment in which it was surrounded by, let's say, 6 oxygen atoms, those d orbitals would divide themselves into 2 different sets. One of the sets, the dz squared and the dx squared minus y squared orbitals, point toward the oxygens along axes at right angles. The other three orbitals, dxy, dyz, and dxz orbitals, point between those axes. And so they end up at different energy levels, one set high and one set low. This is a garnet. It's a distinctly different color. Its iron is surrounded not by 8 but by 6 oxygens, and so it has a different d orbital structure, and it turns out looking brown. It absorbs the blue and the red end and gets mostly the yellows and has a brownish yellow color. The activities and the research and the teaching are that's the icing on the cake.